online physics students, welcome back again. Physics lesson. Today we will see Newton's second law of motion and Newton's third law of motion. Let's see Newton's second law of motion. Newton's second law states that the acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system and inversely proportional to its mass. That means, look, in equation form, the Newton's second law of motion states that the acceleration of a body directly proportional to the force, okay, and inversely proportional to the mass, which means if the net force increases, its acceleration increases because it's directly proportional. And in the same direction, again, the acceleration and the force and the acceleration in the same direction, okay, they move horizontally, or the force and the acceleration for the vertical we will see later when we see the weight, okay. So it's the same in direction as the net external force acting. Here the acceleration is net force over mass. This often in the more familiar form, the force can be calculated by mass times acceleration. If the mass increases, again it says here inversely means if the mass increases, the acceleration what? Decreases. That means mass and accelerations are inversely proportional. Alright, so when only the magnitude of the force and the acceleration are considered, this equation is simply net force is equal to mass times acceleration. Let's see what's inversely and what's directly proportional. Let me show you one simulation. Come on. Okay, here is a simple simulation. Assume here the applied force is 0. Now let me give for the applied force 50 newtons, okay, and let's make the object to start. Let me decrease. Okay, now look, and the object starts to move after applying 252 newtons of force. Now if we add mass here, what will be happen? Look, the speed here, it decreases, yeah, when again I add 50 kilogram. Now this 252 newton, the man applied, is already stopped because of the mass. That means if the speed decreases, there is no acceleration. That means here you can see that due to these two masses we add 200 and kilogram and so these two masses stop the object, okay. That means the speed is here, you see, it's 0. Let us remove the mass, okay, and let's see what will be happened. Okay, let me remove this mass as it is, and this one. Look, you see, the object starts to move, and its velocity is increases speed. Look, the speed it's increasing. This means it's accelerating. That means the acceleration is inversely proportional to the mass. That means if the mass increases, the acceleration decreases. Okay, that's what it says, Newton's second law. And if we increase the force here, we give for the system 252 Newton. If we increase the force, then its speed will increase. Look, 300, now 400. We see the speed, it's increasing. Even the speed here we can't see. Okay, look. You see the speed increase. We give here the 500 Newton. Okay, look, the velocity increase. All right. Sorry, the force of the man is less. Okay, good. Okay, here is another figure that shows these two guys, lady and baby. Let me say they are applying a force. The lady applied F2 and the boy applied, let's say, F1. Okay, that means the free body diagram can be decomposed like this. Okay, F2 and F1. Okay, we can put like this, and here they apply a force, and this trolley is moving forward. Okay, that means the acceleration is directly proportional to what? The force we applied. All right. Units of force. Force has its SI unit, and its formula, you know, force is mass times acceleration, is to find the unit of the force in terms of three basic units for the mass, length, and the time. The SI unit of force is called Newton. Okay, Newton is the SI unit of force. Its symbol is N, and if the force needed to accelerate 1 kilogram system at the rate of 1 meter per second square. Okay, in general, 1 kilogram per meter per second square. Why? You know, net force is mass times acceleration. Net force is equal to mass times acceleration. The unit of mass, as already known, it's kilogram, times the unit of the acceleration is meter per second square. That means 1, which is equal to in Newton. Okay, that means 1 Newton is equal to 1 kilogram meter per second square. All right. The second point, weight and the gravitational force. Okay, when an object is dropped, it accelerates towards the center of the earth. Assume an object dropped from a certain height h, okay, and the object has its own mass. Then Newton's second law stated that a net force on an object responsible for its acceleration if a resistance is negligible and the net force on falling object is gravitational force commonly called the weight. That means this object is down vertically due to acceleration due to gravity. Okay, weight can be denoted as a vector quantity because it has direction part. For example, a foreign body has its direction downward. By definition, the direction of gravity and hence its weight is downward force. Okay. Consider an object with a mass falling down toward the earth. Okay. It experiences only the downward force gravity, which has magnitude weight. Newton's second law states that the magnitude of the net external force on an object is mass times acceleration. This is the second law of Newton. Okay, since the object experiences only downward force of gravity, the net force is equal to the weight. We know that the acceleration of an object due to the gravity is g, or a acceleration is equal to g. Substituting this into Newton's second law, it gives the following equation. That means, let me take this one. This equation, the weight of gravitational can be calculated as mass times gravity. This one is due to the acceleration due to gravity. For the horizontal case, the force is mass times the acceleration. For the vertical, we have for the downward, due to acceleration due to gravity, we have only the weight. Okay, we calculate it by mass times gravity. The weight g 9.8 meters per second on the earth. The weight of 1 kilogram object on the earth is 9.8 Newton. As that means the same thing is what's happening. The SI unit for mass is kilogram. The SI unit for gravity is meter per second square. But one weight is equal to 1 kilogram per meter per second square, which is equal to, weight is equal to, we can write as, for 1 kilogram, the mass is 1 kilogram times acceleration due to gravity 9.8 meter per second square. This gives you what? 9.8 times 1, 9.8 kilogram meter per second square means we already seen that kilogram meter per second square is equal to 1 Newton. That means the same case is equal to Newton. Okay, so 9.8 Newton. Let's see one example. What acceleration can a person produce when pushing a lawn mower? Suppose that the net force push minus friction exerted on a lawn mower 51 Newton parallel to the ground. The mass of the mower is 24 kilogram. What is its acceleration? You have given the force is 51 Newton and the mass of the mower is equal to 24 kilogram. You are required, what is its acceleration? Acceleration is equal to how much? All right. Now the acceleration, force is equal to mass times acceleration. This implies the acceleration is equal to force over mass, which is equal to, in our case, push minus friction. Already, so the force change, the force 51 Newton over the mass 24 kilogram. Then the acceleration is equal to around 2.1 meter per second square. It's simple, okay? Its unit is meter per second square, okay? That's the value of the acceleration. Great. The next point is Newton's third law of motion. Whenever a body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that is exerted. This law represents a certain symmetry in nature. Force always occur in pairs. These two forces, action and reaction force, equal in pairs, and one body cannot exert a force on another without experiencing a force itself. We sometimes refer this law loosely as action-reaction force, where the force exerted is action and the force experienced as a consequence is the reaction. This Newton's third law, the body exerts a force on second body, the first body experiences a force that is equal magnitude in opposite direction. This law is called Newton's law, third law of motion. Okay, these forces always they are equal and opposite in direction. The magnitude, the values of the force equal. Let me show you one simulation which I try to write on. Alright, here is a simple code which I modify using a simple HTML, CSS and JavaScript, and to simulate Newton's third law. Here is the code. Actually, you can do it by yourself. Okay, no problem. Here is the code. Okay, you can use your base code or visual code. And let me simulate this one. And we have these two objects. Okay. Okay. So Newton's assume we have two objects. Okay. And these two objects exert a force each other. This one exerts a force to this object, and this object exerts a force on this object, the second object. Okay, let me change my pen. Right. Assume this. Let me say this is the first object and the second object. Assume this object, the first object exerts a force 10 Newton. Again, the second object exerts again 10 Newton. That means these two objects, they exert a force equal force, but their directions are opposite in direction. That means they are in pairs, these two forces. The magnitude is equal 10 Newton, and yeah, So action and reaction force that appear in two pairs. Okay, so if you exert a force 100 Newton on a wall, the wall again exerts a force on you towards you 100 Newton, equal force but opposite direction. This is about Newton's third law. Okay, let's see the other points. We can really see Newton's third law at work by taking look at people move about. Okay, consider a swimmer pushing off from the side of a pool as illustrated in the figure below. Okay, down. She pushes against the pool and with her feet and accelerates the direction opposite of her push. That means, look again, another practical example. Look here, she push, okay, with the force, okay, then the wall again push her towards the opposite direction. Okay, and the wall has exerted equal and opposite back on the swimmer. You might think that we have two equal force, but opposite force would cancel, but they do not, because they act on different systems. In this case, there are two systems that we could investigate. Okay, the swimmer or the wall. The swimmer is another object and the wall is another object. Okay, so these two opposite forces cannot be cancelled. Okay, cannot be cancelled here at this point. Okay, because they act on this point, different systems. Don't forget this one, or not down. Okay, in this case there are two systems that we could investigate, the swimmer and the wall. Okay, if we select the swimmer to be the system of the interest as shown in the figure, and the net force on the wall is an external force system and affects its motion. The swimmer moves the direction force of the wall on the feet. In contrast, the force of the feet on the wall acts on the wall and not our system of interest. The net wall does not directly affect the motion of the system, does not cancel. Note that the swimmer pushes the direction opposite that which she wishes to move. Okay, the reaction to her push is this direction. Okay, that means she here with her leg pushes, then the wall again push her towards forward. Okay, for her. Okay, so these two forces are equal and opposite direction. Okay, let's see. If you have any question, please comment please, let me see. Okay, yeah, actually it's simple, in our daily activities we can see different applications of Newton's second law, Newton's third law. Okay, we have another example. Okay, a physics professor pushes a car demonstrating equipment to lecture hall as shown in the figure. Her mass is 65 kilogram. You have given the mass of the teacher is 65 kilogram. The cart is 12 kilogram. Mass of the cart is 12 kilogram, and the equipment is 7 kilogram. Mass of the equipment Okay, equipment is equal to 7 kilogram. Calculate the acceleration produced when the professor exerts backward force of the professor 150 Newton on the floor. All forces opposing the motion, such as friction on the curved wheel and a resistance total, is 24. Force of friction 24 Newton. Assume this, we have force of Newton that affects the motion. Okay, now okay, you are required calculate the acceleration produced when the professor exerts a backward force of 150 Newton. Require the acceleration of the professor. Let's see the solution. You know, here we have friction, okay? Friction and a resistance. So we have to find the net force. The net force we have is 150 Newton minus 24 Newton, because this friction affects our force. Okay, so we have to first find the net force, which is equal to 126 Newton. First you have to decompose. If there is no friction, our net force will be equal to 150 Newton. But here we have the net force that affects our force. Okay. The next, we have to find the total mass. The total mass is equal to, you have to add all the mass. That means 60 mass of the total mass. Mass of is equal to mass of the professor plus mass of the cart plus mass of the equipments, which is equal to mass of the professor 65 kilogram plus mass of, say, the cart 12 kilogram plus mass of the equipment 7 kilogram, which is equal 84 kilogram. So we have 84 kilogram. Okay, the total mass. The net force we have 126 Newton. Then the solution. Solution for the acceleration. Acceleration, force, net force over mass. The net force 126 Newton over the mass is 80 for the total mass kilogram, which is equal to 1.5 meter per second square. That is the acceleration, because the net force already here. Why we I see that your comment. Okay, here the professor exerts a backward force. Okay, and there is a resistance force. Okay, this resistance force we call it friction. Friction opposes the motion of an object. Okay, if there is a friction, a little bit it decreases or the speed, or it has effect on our motion. If there is no friction, our motion continues. Okay, that's why when we talk about gravity, we neglect air resistance Okay, so that's why we minus the air resistance and the cards friction. Okay, is it clear? Please say comment. I need your comment, please, 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 on the. Okay, good, now it's clear. Okay, if you have any question, send me. Okay, that's about today's lesson. Not, it's not too much difficult. Okay, yeah, see you in another lesson. Until then, bye bye.